What percent of this entire bin is red? 8? 80? 70? Are you guys with me that just staring at this and trying to make that conclusion is an unpleasant idea? Yeah? So what if I say take a sample and I were to tell you that 18 out of the 22 beads in this sample were red? Would that help us start to make a guess? So we're good? You guys, we got a problem because this one it's only 16 out of 22. Is everybody with me? First it was 18 out of 22, then it was 16 out of 22, 17 out of 22, 16 out of 22. I'm just counting, by the way, I'm not counting the reds, I'm counting the non-reds. And subtracting, yeah. But you guys get the basic premise of this, yeah? So when I take a sample, so we had 18 out of 22, we had 16 out of 22, we had 17 out of 22, we had 16 out of 22. So will I always get the same percent red from my sample? So if what I'm talking about is the percent, the sample's not all the same percent. What about the percent of the bin that is red? Is the percent of the bin that is red always the same number? It just exists somewhere, right? We don't know what it is, but it is only one value, yeah? So when I say will it always be that percent? The samples will not always have the same percent, but the population always has the same percent. Does that feel okay? And is it possible that I take every single possible sample out of here? Theoretically. Are you guys with me that that is an unreasonable thing to do? Okay, great. Because there's actually more samples than there are beads. Yeah? Okay. Now, is it possible? Yes. But not realistic. So what we're going to start to do is think through what we call it, something called a sampling distribution. And I won't expect you to know what a sampling distribution is until we get back from Thanksgiving. But I want you guys to envision kind of like, could I make a graph of all of these numbers and then imagine I did those percentages over and over and over and over again for every single possible sample? Okay? Great. All right. So before we can really get too far into sampling distributions, I do want us to think through, we're going to rely on the normal distribution and the thought processes behind knowing something is normally distributed and what that means. We're going to be going through that a ton. So I want us to be in a place where we can kind of think through and review those ideas, okay? So the weights of hazelnuts are normally distributed with a mean of 1.34 grams and a standard deviation of 0.25 grams. Okay, so if I have a hazelnut that weighs 1.56 grams, what does it mean when I say what is the z-score? What did the z-score really mean? Is a number of standard deviations from the mean. So, will this hazelnut have a positive or a negative z-score, and how do you know? Positive because it is bigger than the mean. So, we could say how far above the mean is it? And then how many standard deviations is that? So a reminder, the formula for z-score is the observed value minus the mean divided by the standard deviation.
Mean is mu, right?
Mm-hmm. As your population mean is mu. We'll talk about that in like 10 minutes. .88. So we could say that hazelnut is 0.88 standard deviations above the mean. Again, the word above or below, kind of important, because we're basically describing. So is that a super big hazelnut? How many standard deviations above the mean do you need to be for something to be kind of like super crazy? It was 2 standard deviations. So I would not call this a super big hazelnut because it's not even a whole standard deviation. It's big, but it's not like crazy big. Cool? All right. Weight is the 30th percentile. Yes, what does it mean to be the 30th percentile?
Isn't it like they're going to be like 70% of population is going to be larger?
Okay. I'm going to just say it is 30% would be lower. Yeah? Which tells me that this area is 0.30. Do you guys remember where in the calculator we can find this? Inverse norm of 0.3. It's actually, that's meant to be that mu symbol. Like, it's a pixelated cursive M, basically, for the mean. But it's because it's pixelated that it's not very good. That feels reasonable to me. 1.21 grams, yeah. Are we all getting 1.21? Everybody feeling good? All right. What range of weights contains the middle 90%? I don't know if we've done much with this kind of thing or not, but So let's start with just drawing where the middle 90% are. If I have 90% in the middle, we're going to start really talking about tails. Okay, we have a right-hand tail and a left-hand tail, right? This is the right tail. It's the tail of the larger values. The left tail is one of the lower values. And what do I know about the area of both of those tails combined? What does it need to be? 10%, right? So what does each of them individually need to be? 5%. So because normal distributions are approximately symmetric, we can assume they're the same. So just divide that 10% in 2. Yeah? Okay. So then what do we tell the calculator? In some respects, like if I want to find this specific value here. Do I know the area to the left of that specific value? It is 5%, yeah? And after that, it's no different than the picture above. We're going to do the inverse norm of 5%. And let's see, give or take 0.88, 0.932. And then this value, what is the area to the left of that value, of the upper one? You guys with me that it is 95%? Because it's the 90% plus the 5% tail. Now, some of your calculators allow you to just put in 0.9 for the center. That's just fine. Just not everybody's calculator does that. So I want to go through the... what are we getting? 1.75. So we would say between, the interval would be between 0.932 grams and 1.75 grams. Okay, new context. The running times of movies are normally distributed with a mean of 102 minutes. At 92 minutes, Aladdin is the 23rd percentile. We want to find the standard deviation. So in this case, for right now, if I don't know the mean and both the mean and the standard deviation, using that function on the calculator doesn't work. So does anybody remember what we did here? We did have some questions like this. Yeah, we can find, because we do know the mean and standard deviation of z-scores. Z-scores always have a mean of 0. They always have a standard deviation of 1. So we can find the z-score associated with the 23rd percentile. And again, knowing something, we need to know it's normal in order to do this, but we can do it. What is the z-score of the 23rd percentile? Negative 0.74? Great. And picture-wise, guys, that means that this distance is 0.74 standard deviations, which also means then that this distance has to be 0.74 standard deviations. Is everybody comfortable with this idea? What is this distance? Like, if I don't think of it as the number of standard deviations, if I look at it on the axis, what is this distance? 10 minutes, yeah? Okay, so I have 10 is equal to 0.74 times the standard deviation. I'm just imagining 1.3 and some change. 1.33? 1.32 maybe? No. 43 and some change. If I do 10 divided by 0.74.
I got 13.5.
13.5. Oh, yeah, okay. Now, if you want to use the z-score formula, guys, we could say negative 0.74. Like if you're more formula-based, the z-score is equal to the 92 minus the 102 over the standard deviation. When you solve this, you're going to end up with the statement 10 equals 0.474 sigma. Like you'll end up there. Okay, so if it's easier for you to think through, I know my z-score formula and go from there, that's fine. All right. Good so far? Fantastic. All right. Now, for pretty much the entire second semester of the course, we're going to be dealing with what we call statistical inference. When you guys hear the word inference, what does that mean to you?
Educated guess or assumption.
An educated guess, great. In statistical inference, how do we educate our guess? We take a sample and use it to make a conclusion about a population. Okay, so statistical inference is using a sample to conclude about a population. And there's lots of different types of conclusions we can make. Okay, so we're going to learn lots of different techniques for statistical inference. All of Unit 5, where we're going from here, all of it, the goal will be laying the groundwork for the thought processes behind the statistical inferences that we will be doing. Okay? So, there's some new vocabulary I want us to start thinking through. Okay? All right. So, in the statistical world, we have parameters and we have a statistic. Okay. A parameter is a number that describes the population. For example, what percent of this bin is red? That's a population. We would use a number to describe it. Could I ask you guys, could we find the mean weight of all the beads in this thing, right? Like if we had a super fine scale, put this on it, I could get the weight of this one, and then this one, and this one. You guys catch my drift here? Right, we could so we have a population mean. Now, a statistic is very similar, except for it is the same number, but it describes a sample. So, for example, when I take this sample, that is 16 out of 22, that is a statistic, because it's a percent of red here, percent of red of the sample is a statistic, percent of red of the bin, the entire bin, is a parameter. You guys catch it? Okay. All right. So, a parameter, one of the things I want us to understand is some sort of unknown constant. So when I said there's only 1% red in here, right? This bin only has a specific, there's only one percentage that describes what percent of the entire bin is red. Okay? Whereas the statistic is a known variable. Calculating the statistic is easy. You take your sample and you calculate it. Okay? We know what it is. Unfortunately, different samples have different values. Okay, so it's a variable. It changes depending on which sample I take. I take a new one, different percent. New one, different percent. Okay, so the percent for each sample is variable. Is everybody with me? But it's known. The percent of the bin stays the same, but it is unknown. Everybody good? Okay, so we have been dealing with some of this already, but I'm going to kind of formalize stuff now, okay? For example, earlier someone asked what the symbol on our calculator was, and I said it was mu, a curly QM, that describes the population mean, okay? So if what I'm measuring, if I have a mean and it's of the entire population, we call that mu. That would be the symbol we use. If I have the mean of a sample that is not from a population, we use the symbol X bar. So X bar is a statistic. There are a lot of different X bars for a population. Mu is a parameter. There's only one mu for a population. This is the actual mean of the population. Again, usually unknown. Okay. Likewise, sigma, and S is the one we use off of our calculator, right? When we describe normal distributions, we're describing the population. That's why we use mu and sigma. But when we think about what we grab off of our calculator when we have a sample of data, we use S and X bar. Okay? All right. Now, we haven't talked about the parameter and statistic we were modeling here, which are proportions. Remember, proportion is the decimal version of a percent. Okay? So, the proportion of a population is P. The proportion of a sample is P hat. All right. Gallup poll asks a random sample of 515 U.S. adults whether or not they believe in ghosts. Do any of you guys believe in ghosts? Yes? No? Interesting. Usually get at least one or two. Okay, so what population is this sample trying to describe? What is my sample?
515 adults in the U.S.
The 515 U.S. adults, which we were told was randomly drawn from all U.S. adults. So my population would be all U.S. adults. What's my statistic? What do we know about our sample? So we would say my statistic is P hat, 160 out of 515. So you guys got 31%, 0.31. And what that P hat is trying to estimate is what P. I'm going to be very particular about when you describe what a parameter is. We're going to call it the true proportion of U.S. adults who believe in ghosts. that pretty good? True proportion meaning like we don't know that it's 31%. 31% is that one sample. The true proportion is the one we don't know, that we're trying to estimate, that we're using our sample to get to that estimator. All right. What if I had a random sample of 318 teenagers who had a mean screen time of 4.5 hours? What's my sample?
318.
The 318 teens. Who are they trying to represent?
All teens.
All teens. What's my statistic? I'm going to call it X bar because it's a sample mean. What was my sample mean? 4.5 hours. And my parameter would be mu, the true mean screen time for teenagers. All right, so towards the end of last week, in fact, that day before we left for Thanksgiving, we essentially had like a 10-minute worth of class, right? You got your sample of starbursts, and we plotted these little p hat symbols. You guys remember doing this? Okay, and so the first thing I want to point out is how come we had different answers?
Just not saying.
Not the same. Yeah. Essentially, all samples are different, right? And, okay. And so when we plotted this symbol right here, like when I look at this one right here, where I have a p hat plotted at 0.4, what does that really mean? To say that p hat is equal, for that one person, to say that p hat is equal to 0.4, what does that mean in context?
40% of their starbursts were pink.
Okay, I'm going to say that a little bit different. Okay, instead of saying their starbursts,
Their sample.
40% of their sample. Is everybody with me? And instead of saying 40%, I'm going to say the sample proportion. Of pink is 0.4. That's what p hat equaling 0.4 would mean. And unfortunately, not all of our samples were 0.4. Some people had a 0.6. Some people didn't get any pinks, right? Is everybody good? All right. And what would, if p hat is the sample proportion, what would p represent?
Population.
The population proportion? Okay. You guys, sometimes we call the population proportion the true proportion. Okay. So this is just kind of reviewing that we have like different symbols for sample values versus population values. What if instead I borrowed Dr. Lee's balances and had you measure the mass of every single one of your starbursts and then you found the average mass of your starburst. Could I have done that? Okay. Then what would we be plotting for each of your...
Would that be R mass or everything's mass? Like, okay, never mind.
So if I gave you 5 starbursts and had you find the average mass, that would be the sample mean. Versus mu would equal the population mean. Now, and again, sometimes instead of saying population, we say the word true, okay?
How would you have a mean of like one like little group?
If what we measured was how much they weigh, right? So you would have, I have no idea what a starburst weighs. I'm going to say 30 grams, right? Okay, so think about your sample when you had your 5 starbursts. You might have had one that was 29 grams, and then 30 grams, and then 31 grams, and then 31 grams, and then 20 grams, 28 grams, right? You would have 5 different masses.
The standard deviation would be the same, right? Between population and sample.
Ooh, no. No. We'll talk about that in just a sec. That's a really awesome question, though. That's a really awesome question. Okay. Kate, did I answer your question?
So like X bar would be the average of like
Of your 5,
It'd be the same.
right? And mu would be like the average of the entire bag. Cool? Great questions. Okay, let's talk about your...
I can't figure it out.
Okay, let's say we talk about the standard deviation of heights in this room. Cool? It has a number. It's probably... Sam, how tall are you?
I'm 6'1".
6'1". How tall are you?
6.
6. Okay. Shortest person in the room.
I believe that might be William.
I don't think so. I bet William's taller than me. Sierra, how tall are you? 5. Okay. Yeah. All right, now, start thinking about the standard deviation of the room is probably about 3 inches. All right, now, we're going to take a sample of 2 people from this room, and those 2 people include myself and Sam. That standard deviation is way different. So, I like how you're thinking about, I love, in fact.
Confuse it with Z-score almost.
Oh, yeah, now the Z-score for anybody is the same no matter how we measure it. Yeah. Okay. Everybody good? So far, we good? Great. Lovely. All right, now, let's go ahead and say that both Mr. Stork and Mr. Belker are trying to estimate how much time students are spent preparing for, say, the PSAT. And so Mr. Belk takes a sample and found that the mean of his sample is 3.2 hours. What symbol would that be? I make these numbers up. I don't know how much you guys prep for the PSAT. It would be a X bar because it is the mean of a sample. Okay. What about Mr. Stork? His sample was 2.6 hours. You guys, why didn't they have the same answer? Both samples from the same population.
Different samples.
The samples are different from each other. Period. Do samples resemble the population? Do samples match the population?
No, but they represent it.
Hopefully. Hopefully they're representative, right? So, this next phrase, you are going to use more times than you want to. I promise. Because I'm going to make you lots of times. It is the foundation for the entire second semester. Everybody ready? So you're going to repeat this with me. You ready? Samples are not perfect. Say it with me. Samples are not perfect. One more time. Come on. Prove to me that I'm hitting this point home. Samples are not perfect. Guys, I believe in this so much.
Samples are not perfect.
I made a button. Okay? And anytime you ask me about certain certain questions, I'm just going to hit.
Samples are not perfect.
You guys with me? Okay. We call that sampling variability. So, you probably have a feel for this already. What we're going to do is formalize it with statistical language. Were any of you guys the group that got the sample with 60% pink? Was that?
I think I did.
Okay. Do you believe that the pinks are overrepresented in the bag?
I guess. I don't know.
Compared to all the other ones? That might make us think this, right? That over half the bag's pink. That's a good bag of Starburst right there. Is it over half of it is pink. But is it true that over half the bag was pink? But it's, all right. So, by chance, we got a sample that was 60% pink. And so, what we got to start to be able to do, and so we're kind of laying the foundation for this right now, is, okay, 60%, like, how do we decide, is this sample that's 60% pink, is that overrepresenting? Is that a crazy thing? What does that actually mean when the sample is 60% pink? Okay? This is all going to be very, very theoretical, and it's not gonna be, oh, I can just draw a picture and work it out. Okay, so we just wanna make sure we're keeping track of theoretical things that are happening here. Now, could I have asked you to put all your Starburst back in the bag and take a sample again and again and again until we have taken every single possible sample of 5 Starbursts? Could we have done that?
Yes.
Okay. Is it a practical thing to do? No. In fact, there's more samples than there are Starbursts. Everybody good? Okay. So, when we talk about this thing that I'm about to talk about called a sampling distribution, it is a theoretical distribution as if we'd taken every possible sample. And we're going to talk about sampling distributions a lot. A lot, a lot, a lot. And in some respects, the reason we do this is to say, where could our sample fit with the population as a whole? That's kind of our idea. So far, are we feeling okay? Okay, can you take out laptops? And in your laptops, I would like you to go to artofstat.com. Everybody good? All right. Now, when you're at Art of Stat, what I'd like you guys to do is scroll down, you're going to click over here where it says Online Web Apps. Go ahead and pick Online Web Apps. And we're going to scroll quite a bit. Till you get to where it says Sampling Distributions in the Central Limit Theorem. Everybody good?
Sampling versus of the what?
It should say sampling, and then you're going to pick the one in the middle that is sampling distribution of the sample mean, continuous population distribution. And you should have something. What else? Unimodal. If we wanted to, we could describe the center and spread, right? Everybody good? Great. Now, what I'd like you all to do, right now, do you see where it says a sample size of 20? And it got this one highlighted? Go ahead and just hit draw sample. And to make sure we understand what we're seeing, how many observations do you think are in this particular histogram? 20. And the mean of this histogram is right here. Also plotted right here. So now, how many of your histograms look like mine? Anyone's? How come? We all got different samples. And do any of our histograms match the population?
Not exactly.
Kinda, maybe. Maybe, close. All right. Now, if I go ahead and hit draw sample again, I got a super different histogram with a different mean. It's kind of hard to see, but I actually have two different ones down here now. Is everybody with me? So this is the mean of my first sample. This is the mean of the sample I just took. Is everybody good? And this histogram for me almost matches that population kind of the same now, right? Do you guys see what I'm saying? Okay. And then if I take another one, a new mean popped in down at the bottom here. Different sample. You guys catch the drift of what's going on? So every time I hit draw sample, a new point comes in here at the bottom. So if I do a lot of these, do you guys see that I am simulating a sampling distribution? Is everybody okay? So I'm kind of getting bored of doing these one at a time. I'm actually going to click this 1,000. Now, how many of your graphs look just like this one? Just like it?
Pretty close.
Pretty close? Okay. Let's go ahead and draw 1,000 samples. Everybody good? Ooh. Here's my most recent one, right? How many of your graphs look really close to this one? And if we did 1,000 more samples? Are you guys seeing? Is this good? I bet we're all showing. How many of you have a graph down here that is skewed to the right? What about your mean and your standard deviation of this graph? Are they pretty darn close to this?
Yeah.
Okay. So, we all took different samples every single time, but our distributions in the long term are all looking pretty darn close, yeah? Because sampling distributions are predictable. All right. So, as we're going to start investigating something called the central limit theorem. I'm going to give you about 5 to 10 minutes to play with this, okay? And there are two things. For all of them, we're going to look at what happens as I increase my sample size. And I want you to look at two things. As you increase your sample size, what happens to this graph? I want you to look at its shape. And I want you to look at its standard deviation. Is everybody okay? What happens to this graph as I use larger and larger samples? Questions? I would like you to do that using several different ones of these populations. Everybody good? I'm going to give you like 5-ish minutes to kind of investigate this, okay?
Can I go to the bathroom?
Bless you.
How do you put that curve on there?
If you go down where it says options down here, and then you can also select which parts of the x-axis you can see so that you can zoom in on the bottom graph. Mine does or yours does?
The one I'm looking at.
Yeah, I was going to say mine doesn't look normal to me.
For these questions on here, should it, college earnings, what sample size should it be?
Well, it's more about, like, I want you to see, like, as I increase the sample size,
I see.
what's happening down here. Okay? And so, like, let's start with the shape. We can use the one I have up right now if you want.
More normal.
Look at my shape right now. Is this normally distributed? Like, when you look at the blue compared to the normal curve, does that look good? I don't think so either. All right, but if I bump my sample size up,
It's close to normal. That's the bigger.
it's getting closer and closer and closer to normal. Is everybody good? And let's see if that's true for a different distribution. Let's look at Airbnb prices. Okay, and I'll start with, again, a small sample size. Kind of hard to tell if this is normal or not. Let's kind of do this again. Kind of hard, like I can kind of see, when I look over here, I can see this is mostly under and this is mostly over, which suggests a little bit of a tail. Okay, all right, but if I bump my sample size up, starting to look better and better and better. Is everybody good? All right, so let's talk about why for a second. All right, so I'm going to keep my sample size I'm going to put it at 50, and I'm going to reset everything, and I'm going to start selecting one sample at a time again. And what I'd like you guys to do is I'm going to do it one at a time, and I just want you to keep an eye on two things, the X bar here and the histogram itself of the actual sample itself. Okay? So there's that one. If I draw a different sample, what's happening to this X bar? It's kind of bouncing back and forth a little bit, right? What about the shape of this graph? It's skewed right. And in fact, as I compare this graph to the population, it's feeling pretty darn close. Is everybody with me? So for a large sample size, what's happening is the sample kind of matches that population, and that mean of the sample is going to fall relatively close to the population mean. Does that feel okay? Great. Now, if I use a smaller sample, 10, we're going to do the same thing. And again, I just want you to watch that graph. Again, you're looking at the X bar and the shape at the same time, okay? Are the shapes as consistent? And what about that X bar? Still jumping around, but it's jumping around a lot further. Why? Because the samples are less likely to represent the population. Are we feeling okay? And if you were to start to think about, every time I take a sample, the mean kind of falls down onto this graph. Are you with me that we're getting about as many sample means above the mean, above the true mean, as below the true mean? I'm going to keep doing this and doing this, okay? Okay, so I'm going to get to, let's use this one, that's perfect. This is a really good example to stop at. Okay. All right, so as my sample size increases, if I call this are we comfortable saying this sample does not represent the population well? Okay, so smaller sample sizes lead to higher chance that we get kind of this not great sample. Is that okay? Okay, but so larger samples are more likely.
If you're writing on it, we can't.
Oh, yeah. Larger samples are more likely to represent the population. Okay? And so what happens is once you take the mean of that sample, or if we were even looking at, say, this one, it wasn't crazy to get a 60% when my sample size was 5, but it was crazy to get a sample of 60% when my sample size was 10. Do you guys get what I'm saying here? Okay. 5, you were very likely to, not very likely, but it wasn't unlikely that you got a non-representative sample. 10, your sample was more likely to represent the population. Everybody good? Okay. So, the p hats or the x bars are more likely to resemble p or mu, respectively.
As the sample gets larger.
Say that one more time.
As the sample gets larger.
Yeah, for larger samples. Yep. Okay. So the big idea there is twofold. Because the p hats are getting closer to p and the x bars are getting closer to mu, they're much more predictable. And predictability almost always ends up with this very lovely shape that we like to use a lot in the statistics world. It is the normal distribution. Okay, so larger samples, as n increases, sampling distributions get closer to normal. Okay. What happened to the standard deviations as you guys increased the sample size?
Smaller.
They got smaller? Yeah? So as n increases, sampling distributions are less spread out. All right. Why would I care? Why do we care about something being less spread out? Okay. The purpose of learning about sampling distributions is so that we can make conclusions about a population. Okay? We're using our sample to make an inference about our population. If that's the case, wouldn't we want our sample values to be as close to the population value as we can? You guys with me? Which one of these would you rather use to decide what percent of that bag of Starbursts was pink? Which one's easier? Makes you more confident in your selection? This one or this one? The top one?
Bottom
The
ten.
10. Sorry. N equals 10. Why? It was less spread out. These ones make me very unsure about 25% being what it was. This one makes me pretty confident that it was probably about 25% pink. Everybody good? And why is this one better? Because all of our samples were much closer to that value we're trying to estimate in the first place. Okay, so if either X bar or P hat is less spread out, if the X bars or the P hats, because those are our variables, is less spread out. Hey, anybody who's good at grammar, if X bar, I think it should be R.
Yeah, it should be R.
I think when I said X bar singular, it was is, but when I changed it to X bars, it became are, I think. If X bars or P hats are less spread out, then our X bar or P hat is closer to the true value in the first place. By the way, that true value is
P.
mu or P, you're right. We're almost done, I promise.
You have a lot.
We're almost done with today. In fact, similar to what I have up when we do this. How are we feeling, okay? Great. And let's go ahead. What I'd like you guys to do is pick, let's do, distances of New York City cab rides. Or taxi rides. So where it says select example, distances of New York City taxi rides. Okay, here's what this website does. It is not reasonable for us to take every possible sample, correct? This does it quickly and fast for us. It takes samples, measures it, takes samples, measures, takes samples, measures. So for right now, what are some things we might notice about our population? If I asked you to describe what you see in this population, you would say? Skewed to the right, for sure. Okay. We're doing this today, and then we're going to be done. Yeah.
Is quiz at our last quiz for the
Yeah, there's another homework, but there's not another quiz.
Actually,
Okay. Now, a statistic is considered an unbiased estimator if the mean of its sampling distribution is equal to the true value. Now, I'm going to go back to my laptop for a second. Come on. Okay, I'm going to take my sample. Make it a reasonable one. Okay, in this case, my sample mean is landing to the right of my population mean, yeah? So in this case, the sample mean's a little bit bigger than the population mean. If I draw another sample, still a little bit bigger, but like closer, smaller, 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 bigger, and we keep going. Do we feel good that the X bar is kind of dancing around that population mean? Doesn't that make us feel really good about using that sample mean to estimate the population mean? Okay, and the mean of our population was 23,708. Are you with me that the mean, if I keep drawing these samples, it's like the mean of this distribution is staying right there, because X bar is what we call that unbiased estimator. The sample mean is going to be pretty darn close to the population mean, sometimes a little above, sometimes a little below. Cool? Is that true of everything that I could measure on my sample? For example, if I did the range of my sample. And this will be hard to envision. But back to our heights, Sam's 6'1", Meister's 5'1", so the range of the heights of the people in this room, give or take, 12 inches. Yes? Are we ever going to take a sample whose range is bigger than 12 inches? How is that going to happen? Of people from this room, are we ever going to take a sample? If we are the population, will our sample range ever get bigger than the population range? Will it get smaller than the population range? So, are you guys with me that the sample range is likely to underestimate the population range? Yeah? So it's a biased estimator. I would not want to use the sample range to estimate the population range. Cool? It's biased. X bars and P hats are not biased estimators. Okay? We'll spend almost all of our time talking in some capacity about X bars and P hats, and we love them because they are unbiased estimators. You would expect to get as many samples whose mean is below the population mean as you would above. Likewise, if I go over here, we wouldn't expect every sample to be 25%, but we'd get a few above 25%, a few below 25%, and on average they would be 25%. Everybody good? All right. When we talk about biased estimators, it's basically, am I using the right statistic to represent what I'm trying to represent? This is not the same thing as bias in a study. Like in, it's not the same thing as I had a poorly designed study. Okay? All right. So, if the center of my sampling distribution is either mu or p, and I'm estimating p hat, or I'm using X bar to estimate mu. If I have less variability in the sampling distribution, i.e. larger sample size, less variability. Larger sample size, p hats are closer. Sample represents my population better. Okay. The p hats will be closer to p. Or the X bars will be closer to mu. Done. Okay. All right. So today we're going to start talking. Last few weeks we've been kind of talking about the concept of what is a sampling distribution. Today we're going to talk about very specific sampling distributions. So the first thing we're going to do is just kind of reacquaint ourselves with something that will end up coming back on the test next week anyway. It is looking very likely that the Unit 5 test is going to get bumped till Friday. I just don't see how we're going to get through everything next week. I'm going to try, but it's very likely your test will be on Friday instead of on Thursday. Okay, so let's say, how many of you guys have heard the statement or something similar to, if you flush ice cubes down the toilet during a snowstorm, we're going to has anybody ever flushed ice cubes down the toilet? Does anybody have any other snow day superstitions?
PJ's inside out, spoon under your pillow.
Those are the two I hear the most.
A white crayon on the
A white crayon on the windowsill? I don't know that I've ever heard that one.
I saw it, like, I don't know. I've never done that one. All the other ones, absolutely. Elementary school, I was all in.
Oh, for sure. I have one that it was more when I was a student than now, but it was for sure I had to do all my homework. Because if I counted on the snow day, it never worked. But if I had all my homework done,
That makes sense. If you don't think about it, it happens.
something about Murphy's Law. You guys know Murphy's Law? Anything that can't go wrong will go wrong. So, like, you have to get your homework done because otherwise it's going to go, what could go wrong? The snow day doesn't happen and it's going to go wrong. Yeah. Okay. You guys. So first question. Agreement with this statement. Is it a categorical or quantitative variable? Right? Categorical or quantitative?
Categorical. It's whether
Good, yes or no. They agree with it or not.
Quantitative. Thank you, Mrs. Turner dropped them up. One of the Yates twins, I think, made them.
We're all debating the class we should go to.
Really?
Someone said your room needed some more stuff.
Yeah, it's not super colorful. I try, but you know. Hey, okay, so this is a categorical variable. And are we in agreement that there is a difference between categorical and quantitative variables?
I forget.
Categorical is your words are typically responses or category or words or categories. Quantitative means it is a quantity, like a number is your variable. Yes? So for each one of you, I would say, hey, do you agree with the statement?
Yeah.
Do you agree?
Yes.
Yeah.
Yep.
One of you guys uses logic and the other one uses you get the rest of you use your heart. That's great. Okay. So could I measure the mean of your guys' responses? No. In fact, what would I use to measure your responses?
Like tallies.
Or yeah. But at the end, if I needed to summarize what just happened, would you say, I don't know, roughly 9% of you said no and 91% of you said yes? Are you guys with me? Okay, so we use proportions to summarize categorical variables. This is going to come up a lot. Okay. Does that mean that proportions are different from means? Yeah? Are we all comfortable with that? Okay, I got one more comment before I pass back your quizzes from yesterday. So if Mr. Belk is trying to estimate the proportion of students who plan to travel over winter break, he would want a larger sample size so his sample proportion is closer to the population proportion, not so that his sample mean is closer to the population mean, because you would not have a mean percent of people who are traveling for break. You would have you wouldn't have a mean. You guys get what I'm saying here? So I'm going to pass back your quizzes, but if what you are measuring from your sample is a proportion, a larger sample size would mean your sample proportion is closer to your actual population proportion. And the caring of that language is very, very, we have to be very meticulous about what we're measuring.
Is that an I or a P?
Well, this isn't, that would be probably an I. Using the word mean when you need to say proportion.
Well,
Yeah. say proportion and vice versa will definitely probably result in an I instead of a
Well, I
P.
just remember
Like it's one of those like really big
on the
errors.
quiz review, like mean was underlined. I used
So
mean.
if this were a pre-response question, it would be minus like 25% of your grade, right? Maybe 50%. It costs you a point because that's why you don't get the curve on quizzes, because quizzes are not graded nearly as rough.
Because all the quiz reviews we had mean underlined, and then she had proportion underlined. So I was like, no, just.
So if you got every other question correct,
You got
you got that, and on like a test, and you got that,
Yeah,
instead
and I got
of B, you get like.
Well, so like if
you
it
fail
were
that test, and you get-
if it was a 3-part FRQ on the AP exam, on that FRQ you would get a 2 out of 4
Oh yes, okay. That
instead of, but like, which knocks you, but like had you used the word proportion, you would get a 4 out of 4, so it knocked you down to half credit on that
on
particular
that
question.
particular question,
Correct.
not on the test itself.
I think we're kind of even, you're just.
This is really sad. I saw the proportion underlined and folded and I was like, hey, proportion. And then I didn't know what to do about it.
It was by far the number one mistake. And you guys, it is every year. And what did I do to try to help you not make it? I underlined it.
I feel like we didn't learn that.
Yeah. I was just like, well, it's the same.
Well, that's the same right now.
The mean. It's just proportion.
No, the whole point is, it is not the same thing.
No, I meant the same. The question was the same with proportion instead of mean. Yeah, I think
Did I give you the wrong one?
No, I legit wrote the exact same thing. And I just with me. Yeah, that's what I did. I sat on that question for like 25 minutes though. I was like, huh.
What's your grade? Doesn't matter.
Now, in the future, you're going to have to choose between, should I be describing or summarizing my data with a mean versus should I be doing that with a proportion? And the answer to that is you look at individual variables and you say, overall, are individual responses in my sample categorical or quantitative, okay? All right, so last week we talked about the concept in depth about what a sampling distribution of sample proportions looks like. So let's go ahead and say 40% of Grandview Heights high school students agree with this statement. When I say that 40%, is it a P or a P hat? Is it describing, well, how do I decide between P versus P hat? Is it describing a population or is it describing a sample? Since I say this is all Grandview Heights students, it would be a P. Okay. So now